Next thing we're going to move on to is the distance between vectors. And so the idea is if you have a vector x and another vector y, remember that we don't actually care where you place them, so we can place them someplace where they have the same starting point, and then what we are going to do is try to find the distance between the two tips of the vectors here. And it turns out that's a really simple formula. It's just going to be the length of the difference of the two vectors. So you just subtract them and then go ahead and take the length of that. And you in fact can do that in either order without mattering. And the reason why is because the absolute value of, or the norm of, -1 times this difference is the same as the absolute value times the original vector, and the absolute value of -1 is 1. So it doesn't matter which order you subtract them in, you will always get the same distance between them, and that can be useful for trying to find out, where you're talking about in a given geometrical problem. Related to this, but separate, is the idea of the dot product of vectors. This is another thing that you should have seen in Calc 3. And we'll start with R2 here. So let's suppose I have a vector x, which is AB, and a vector y, which is CD. Then we define the dot product of x dot y by taking the corresponding components and multiplying them with each other and then adding them up. And I do want to point out, I see a lot of students in exams, they mess up between determinant of matrices and dot product. On the dot product you are adding these terms, whereas on a determinant of matrix you will be subtracting them, so try not to get those two things confused. Regardless, when you first see this formula and you first learn how to do dot product, it's like, okay, I can follow the rules, but what does that tell us? Well, what you can do is you can do a little bit of geometry, and I'm not going to do all of that here today, but if you do a little bit of geometry, you can prove the following fact, that if you dot product these two vectors, it works out to be the same as if you multiplied their lengths and multiplied that times cosine of the angle that is between those two vectors. And it's not that complicated of geometry to work this out, use a little bit of trig and so on. I just don't want to take the time for it right now. The thing is, we can prove this easily in R2. You can prove it a little bit more difficult in R3, but it turns out that it actually works in any Rn. So the idea is, if you have any Rn, and you have a vector x, which is x1, x2, and so on, and you have a vector y, which is y1, y2, and so on, then you can take the dot product by doing this same rule here of looking at corresponding components, multiplying them together, and then adding the results. And if you just follow this rule, it will turn out that x dot y is the same as the length of x times the length of y times the cosine of the theta between them, even though we can't actually really draw in, say, 5 dimensions or 10 dimensions, this formula still holds true. And so anytime you are asked to find the angle between two vectors, that is the formula you want to use. So let's go ahead and do that now. Let's find the angle between the vector x, which is 1, 2, 3, 4, and the vector y is 5, 6, 7, 8, and these vectors are in R4, and they do have to be in the same vector space R4 here. Otherwise, it wouldn't make any sense. So we'll go ahead and do x dot y here 1 times 5 plus 2 times 6 plus 3 times 7 plus 4 times 8. 5 plus 12 is 17, plus 21 is 38, plus 32 is 70. We also separately calculate the length of x. That's going to be the square root of 30. And the length of y, let's see here, 25 plus 36 is 61, plus 49 is 110, plus 64 is 174. And so then we can, solve for cosine theta by just saying it's x dot y over the length of x, length of y. That would be 70 over the square root of 30, square root of 174. And then we just do cosine inverse here. And put this into our calculator. And so we are going to get I'm getting 0.25 here. Of course, we have to know what mode we are in, and that right there is in radian mode. If we prefer our answer in degrees, it would be 14.3 degrees. Now in calculus, we really care about using radians, but in this class, we're perfectly fine with degrees here.